In this video, I'm going to show you how to calculate velocity for plane motion using differentiation. Imagine that we have a particle moving along some path in the xy plane. Say the path goes from here and then makes a curvy path down to here. The particle has different locations at different times. Say, for example, at t equals 0, at 0 time, the particle might be right here. And then so it keeps on traveling down, maybe at t equals 1, it's over here. And then maybe finally at t equals 2, it's over here. How can we say where the particle is at any moment in time? Well, we just define a vector, say r of t, that tells us the position vector of the particle. That is, where the particle is relative to the origin and the coordinate axis. So the vector r at t equals 0, that would just be pointing from the origin to the particle's position at t equals 0. So here we go. Here's the vector, and we can write that as r of 0. Likewise, at t equals 1, here is the position vector r pointing from the origin to the point, and we can write that as r of 1. Lastly, at t equals 2, again we've got our position vector pointing from the origin to that point, and we call it r of 2. So we see that the vector r is a function of time. The particle changes position as time goes on, and it has an x component and a y component, which we can think of as x of t and y of t, respectively. So this really means that the x-coordinate varies with time, and the y-coordinate also varies with time. And you can tell that from this example graph. As time goes on, the x-coordinate is increasing. Initially, it's at a very small x-coordinate, then it gets to a larger x-coordinate, and it keeps on moving in the positive x direction, so x is getting bigger and bigger. Whereas y, it's starting at a relatively big y-coordinate, but then the next point is at a smaller y-coordinate, and then an even smaller y-coordinate. It seems like the y-coordinate is approaching 0. So the x and y coordinates are each changing with respect to time. They are each functions of time themselves. Okay, so how can we calculate the velocity of the particle? We know that velocity is the derivative of position, but now we're working with vectors. So how do we calculate velocity with vectors? Well, the answer is really nothing changes. We just take the derivative of the position vector, and I'll explain more on that in a moment. But let's write this down to start with. Velocity at time t is equal to the derivative with respect to t of the position vector. And what that really means to differentiate this vector, this position vector, with respect to time is it means that we differentiate each component with respect to time. Each component, x of t and y of t. Each of those is a function of t. So we can take the derivative dx dt and dy dt. And we end up with another vector. And that vector will just point in the direction that the particle is moving at any particular moment in time, with magnitude equal to the speed of the particle. So for example, at time equals 0, our velocity vector would be pointing in the direction of motion, which is tangent to the particle's path. So it would look something like this. So that vector, that would be v of 0, the velocity at time 0. And then the next velocity vector, at the point t equals 1, that would again just be tangent to the path of the particle pointing in the direction of motion. So it would look something like this. There is velocity v of 1, and then finally, at time t equals 2, our velocity vector would look like this, v of 2. So the big takeaway here on this first slide is that the velocity vector is the derivative of the position vector. And ultimately, that just means that we differentiate the position vector, we differentiate each component of the position vector, the x and y components, with respect to t. So we get that the velocity vector is itself, well, a vector of two components, one component related to x and one component related to y. The x component is the derivative of x with respect to t, and the y component is the derivative of y with respect to t. In other words, the velocity vector consists of the velocity in the x direction and the velocity in the y direction, just wrapped up into a single vector. So this right here is the big important formula. Alright, let's move on to a problem. So we're told that the position vector of a particle is given by r of t, which is the vector consisting of components t and t squared. And we want to find out what is the velocity vector, and also what is the speed of the particle at t equals 1. But first of all, let's just worry about finding the velocity vector. So remember that the velocity vector is just the derivative of the position vector. So velocity is dr dt, where r is the position vector. And the position vector is a function of time, so that means so is the velocity vector. So velocity at a particular time t is the derivative of the position vector at a point t. And the position vector, we're told, is just t squared as its x and y components. And what it means to differentiate this vector is really just to take the derivative of each component separately. So d over dt of the first component, t, and then d over dt of the second component, t squared. And then we take those derivatives, so v of t is equal to, derivative of t is just 1, derivative of t squared, using power rule, that's just 2t. So there we go. This is our velocity vector, 1, 2t. Now, before we go on, let's just check that this result makes sense graphically. So let's go ahead and plot the position of the particle on a set of axes. Alright, so to graph this situation, let's start by graphing the position vectors. How about at t equals 0? What is the position vector at t equals 0? Well, position vector is just equal to t squared, so 0, 0 squared. And then let's get a couple more as well. So how about the position at t equals 1? R of 1 is equal to 1 squared, so just 1. Then R of 2 is equal to 2 squared, so 2, 4. And then R of 3 is equal to 3 squared, so 3, 9. So let's go ahead and plot these on the graph. So now on our graph, we've got R of 0 at 0, 0, R of 1 at 1, 1, R of 2 at 2, 4, and R of 3 at 3, 9. And based on that, we can kind of make out the path of the particle. It looks like it's following a parabolic shape, kind of like this. Let's just draw that in for reference there as we start to compare the velocity against this path. Now let's get some velocity vectors. So at time t equals 0, v of 0 is equal to 1, 2t, so 1, 2 times 0, so 1, 0. And then v of 1 is equal to 1, 2 times 1. V of 2 is equal to 1, 2 times 2, so 1, 4. And v of 3 is equal to 1, 2 times 3, so 1, 6. And we'll go ahead and draw these in the graph as well. So indeed we see that the velocity vectors represent the direction of motion of the particle. They are tangent to the path of the particle at every single point, and their lengths represent the speed of the particle. The lengths of the vectors are getting longer and longer, so the particle is speeding up as it continues on its parabolic path. Okay, so our velocity vector makes sense, and now what is the speed of the particle at t equals 1? Well, the speed at t equals 1 is equal to the length of the velocity vector at t equals 1. So the magnitude v of 1. And we know that the velocity vector v of 1, that's just equal to 1, 2. We computed that earlier. 1, 2. And the magnitude of that is just the square root of the sum of squares of components. So square root of 1 squared plus 2 squared, which is the square root of 1 plus 4, which is the square root of 5. So there we go, that's our speed, square root of 5 units per second. Next question. The position vector of a particle is given by this vector r of t, which has as its first component t cubed over 3 minus 2t squared plus 3t, and as the second component t squared minus 6t. We want to figure out at what times is the particle stationary. So let's talk about what that means. What does it mean for the particle to be stationary? Well, that means the particle isn't moving at all, which means there has to be no velocity in the x direction and no velocity in the y direction. So let's write that down. Stationary when the velocity vector is equal to 0, 0. Zero velocity in the x direction and zero velocity in the y direction. Both components of the velocity have to be 0 in order for the particle to be stationary. Okay, so with this in mind, first we need to compute the velocity vector of this particle. So let's do that over here. V of t, velocity at times t, is equal to the derivative of the position vector, so dr dt, and then we'll plug in the position vector into that expression, so d over dt of the position vector. Position vector is just t cubed over 3 minus 2t squared plus 3t as its first component, and then t squared minus 6t as the second component. And to differentiate this vector with respect to t, we just differentiate each component separately. So first, derivative of the first component, derivative of t cubed over 3, well, that's just 3t squared over 3, which simplifies to just t squared. And then minus the derivative of 2t squared, which is 4t, and then plus the derivative of 3t, which is just 3. Onward to the second component, derivative of t squared minus 6t is just 2t minus 6. So that is our velocity vector. Now again, when the particle is stationary, we need this vector to be equal to 0, 0. Now how do we solve this vector equation? Well, we just set the components equal. So t squared minus 4t plus 3 has to be equal to 0. And the second component, 2t minus 6, also has to be equal to 0. So let's go ahead and solve. This first equation is a quadratic, which factors nicely. Factors into t minus 3, t minus 1 is equal to 0. So t minus 3 equals 0, or t minus 1 equals 0, which means t equals 3, or t equals 1. And then the second equation, we can just solve this. It's a linear equation. So add 6 to both sides, get 2t equals 6, and then divide by 2 to get t equals 3. Now, since we need both equations to be satisfied, we need to choose t equals 3. At t equals 3, both components are 0, whereas at t equals 1, only the first component is 0. The second component would not be 0. Actually, if we plugged in t equals 1 into the second component, we get 2 times 1 minus 6, which would come out to negative 4, which is definitely not 0. So there we go. We know that the particle is stationary at t equals 3. That is the only time when its velocity vector is the 0 vector. So now we know how to calculate velocity for plane motion using differentiation, and we know how to find the times when a particle is stationary. In the future, we'll continue working with vectors and motion, and in particular, we'll also learn how to calculate acceleration.